So today we will be talking about nuclear chemistry. I am in Module 7. Module 7 on exploring chemistry. And who can tell me what's nuclear chemistry addressing? Anybody read that much? Is it anything like we've seen before? We are going to need to go back to concepts that we addressed in Module 2. So in that sense, maybe, yes, we'll address those. But it's really a totally different topic to what we have seen in the past. Okay, we started the course saying that we're studying chemistry. Chemistry is the study of matter. So we define matter as anything that occupies space. We went ahead and classified matter into pure substances and mixtures, and we have studied in Module 2 pure substances such as elements. We looked at the elements, the protons, neutrons, electrons. We'll review that today. We said that elements mingle to form compounds. That was Module 3, and we looked at ionic compounds in which electrons from the valence shell were transferred from the metal into the nonmetal. Yes? We studied covalent compounds also in Module 3. And electrons from the valence shell were now shared to form covalent compounds. We had single bonds, double bonds, triple bonds. Then we looked at Module 4, chemical reactions. So everything that we've seen today, that we will be seeing today, is different in the sense that we're no longer looking at elements mingling because of the valence electrons. We are looking at changes that the nucleus is taking place. Okay, so we do need to revisit early concepts, but it is a totally different approach to what we have seen in the past. Today we will discuss nuclear chemistry. First we will give an introduction on nuclear chemistry, and the introduction will address things like what are the different types of radiation that we will be looking at. Then we'll move on to nuclear reactions. And finally, we'll wrap it up talking about time constraints, time elements under an umbrella called half-life. Okay, so let's start with an intro. And in order for us to do that, again, I am in Module 7. Are we all in 7? Reviewing some concepts from the past. Remember when we talked about isotope symbol? Yes, we remember this? If I gave you uranium 238, what did the 238 represent? The mass number. Very good. And if it's uranium 238, what do I put down here? 92. And why do I put a 92? What does a 92 mean? That's the atomic number. Is the atomic number in the chart? Yes, it's in the chart, and it represents number of protons. Okay, and this is in the periodic chart. In the periodic chart. Okay, so the periodic chart has been constructed in order of increasing atomic number. Yeah, we said that. And this top number, the mass number, represented what? What is this? Number of, I can't hear you, protons and neutrons. Is the mass number in the periodic chart? No, not in the periodic chart. Okay, so we said all these things before. But we use the isotope symbol, which is also called the nuclide symbol, to elucidate the number of protons, neutrons, and electrons in a specific isotope. So if I ask you, tell me how many protons, neutrons, and electrons are there here, what do you say? Number of protons? 92. Number of electrons? 92. Number of neutrons, how do I get that? 238 minus 92, and that gives me what? 146, which gives me neutrons. So up to here, we remember, nobody's lost. We're all in the right place. Okay, so today's lecture is going to refer to certain elements, hot elements, radioactive elements. And in these elements, the nucleus. And in the nucleus, we have, what do we have in the nucleus? The protons and the neutrons. Are the electrons in the nucleus? No. Electrons are in different energy levels, and we learned all about that. So we're going to be looking at what happens when elements like uranium-238 undergo nuclear decay, and it emits radiation. What types of radiation are possibly going to be emitted by these hot elements? Some elements after atomic number 90, so if we look in our charts, we need the periodic chart out for this lesson. This lesson requires your periodic chart out. Elements after atomic 90 many times are radioactive. I don't mean by to say that the lighter elements are not radioactive. Hydrogen, which is the very first element in the chart, have radioactive isotopes. There's a hydrogen 1, a hydrogen 2, and a hydrogen 3. Hydrogen 1, hydrogen 2, and hydrogen 3 are three isotopes. Oops. Three isotopes of hydrogen. And hydrogen 2 is deuterium. This fellow is hot. Hydrogen 3 is tritium. That guy is hot as well. So they're radioactive. Okay, but there are some other elements of hydrogen, the most abundant one, hydrogen 1, that is not radioactive. Okay, so some elements appear in more than one isotopes. Some of these isotopes may be radioactive. Okay, and if I ask you protons, neutrons, and electrons, how many neutrons do I have here? Neutrons. 0 neutrons. How many neutrons do I have here? 1. How many neutrons do I have here? 2. They all have 1 proton, right? They're all hydrogen. They all have 1 electrons. But isotopes differ in the number of neutrons. Yes, we remember this concept? And certain isotopes in an element may be radioactive, and some others may be stable. So stable means they don't change. Radioactive means they undergo nuclear decay. The nucleus is changing, and in changing they turn into another element. Okay, so this is a totally new deal. We haven't seen this in the past. It's not the valence electrons that are reshuffling at all. It's the nucleus that are undergoing change. So far so good? Any questions so far? Okay, so let's look at what types of radiation are we going to be addressing. There are 3 types of radiation that we need to consider. And these types of radiation are going to be given Greek letters. Are going to be alpha, beta, or gamma. Okay? Now I am going to give you a little chart to differentiate between these 3 types of radiation. These are the only 3 that this course requires us to learn. And since most of us are visual learners, I will give you an example as to how to relate to in this different types of radiation. If you look in your chart, helium, where's helium? Is helium a heavy or a light element? Where's helium? Top right. So if I write helium 4-2, how many protons is this guy going to have? 2 protons. How many electrons? 2 electrons. How many neutrons? 2 neutrons. So imagine helium, and now I'm going to remove from helium both of my electrons. So I really have no electrons. Okay, an ion +2 of helium. That would therefore be positively charged. That is going to be equated to an alpha particle. So an alpha particle, for us, let's think of the nucleus of helium. Now I'm lazy, most books are lazy, so this +2 part, many times it's not going to be shown. Okay, we mean that, but this is what we're going to write. Helium 4,2, meaning alpha. And really meaning, if we are going to be very correct and very precise, helium 4,2 without +2. Okay, we're just not going to write the +2 because it's cumbersome to write all these exponents and pluses and minuses over and over and over. Okay, so the name for alpha, Greek letter alpha, could be equated with He for helium 4,2. What charge is an alpha particle going to have? What do you think? Positively charged. These are very light particles, so if we are to shield ourselves from an alpha emitter, from an isotope that's shooting out, emitting alpha, a very thin piece of paper would be enough. Very thin clothing. In Miami, we wear t-shirts. That's enough. That's enough of a protection. So I'm talking about the name alpha particle. I am talking about the charge, and in the case of alpha particles, it's positive, yes. The symbol is going to be He42 or alpha. Do I make this bigger? Yes. Is that better? The shield, paper or clothing, that's good enough. The distance that an alpha particle usually travels is 1 or 2 inches, 2 or 4 centimeters. So it doesn't travel, it's not very penetrating at all. Okay, so we're looking at the charge, the symbol, the shield, and the distance to characterize the different types of radiation. The second type of radiation that we are going to look at is beta. And beta, I now want you to think of very fast moving electrons. Okay, so if we have electrons, we're thinking negative particles, very, very light. When we talked about in module 2 early in the course about protons and electrons, we said electrons are 2,000 times lighter than protons, 2,000 times lighter than neutrons. So we called it mass of 0, not because it's 0. Electrons do have a mass, but it's very little. It's a very small mass compared to that of protons. So I want you to equate a similarity between beta particles and very fast moving electrons. So let's try to make it bigger again. The charge is negative. When we talk about beta, we symbolize them as E0 minus 1 or beta. If a beta emitter is next to us, if we have a piece of wood, that would be enough of a barrier to shield us from a beta radiation. Heavy clothing, if you have a coat or a sweater, very unlikely for us to have a coat or a sweater in Miami in September or October. But if you had that, that also is enough of a shield. Beta travels 100 times further than alpha. We remember that there's 100 centimeters in a meter. Okay, so alpha traveled 2 centimeters. This is traveling 2 meters or 3 meters. So it's much more penetrating, but still not so bad. Okay, so beta is our second type of radiation. They're negatively charged, and think of beta as very fast moving negative little electrons, very light. So far so good? Keep moving. The third type of radiation is gamma. Okay, gamma is represented by the Greek letter gamma. This is gamma. Gamma has no charge. It's not positive, it's no negative, it's neutral. It has no taste, it has no color, we cannot see it, but it is very, very strong. Okay, if we are close to a gamma emitter, an element that's shooting out gamma, in order for us to protect ourselves, we're going to need very heavy wall of concrete or maybe lead. When you go to the dentist and they are going to take x-rays on you, the technician goes on the other side, and the other side of the wall, doesn't he or she is not next to you when you're shooting x-rays, and the rest of your body has a lead apron. X-rays are very penetrating, so are gamma radiation. I'm not saying that x-rays are gamma. X-rays are man-made, and these types of radiation, alpha, beta, and gamma, these are all naturally occurring. These are not man-made. These are all naturally occurring. They occur naturally. Elements just shoot them out spontaneously. X-rays are made by man. The only reason I mention X-rays is because you can think of X-rays and they're very, very penetrating. You know, they can get all the way to your DNA. And they can travel 500 meters. So this is 2 to 4 centimeters, alpha. This is 2 to 3 meters, so it's 100 times more penetrating. But this is, again, a factor of 200, 300 more than the beta. Okay, so those are the 3 types of radiation that we will consider today. Any questions so far? Okay, so after the types of radiation, we're ready to go to nuclear reactions. How do we put this in a context of what's happening as these radiations are being emitted? The first concept, when we hear reactions, in the past we put reactants, and after the arrow we put products, right? This is in the past. Well, in this chapter we're not going to do this. Now in nuclear reactions, before the arrow we're going to write a parent, hot radioactive isotope that's shooting either alpha or beta or gamma or a combination of it. So it's not going to be called reactant, it's going to be called a parent. Okay, and then we are still going to write an arrow, and after the arrow we're not going to write products, we're going to find a new term, and it's called a daughter. And I have no idea why they call it a daughter and not a son. I didn't invent this, so I'm just conveying the information. It's either alpha being shot or beta or gamma, but a new element is produced, and this is totally different than what we have seen. Okay, so nuclear reactions, we're going to have still an arrow, but before the arrow is a parent. This is the hot radioactive isotope, and after it emits alpha or beta or gamma or a combination of these, a new isotope is formed, and that new isotope is called a daughter. Okay, if my parent, a minute ago I had uranium-238, right? And I gave you uranium-238, uranium-238. And if I give you that, you're going to say, okay, it's uranium, and the 238 goes on the top, and I have ammunition to write, what was it at the bottom? 92. Well, this fellow, uranium-238, it's an alpha emitter. It emits alpha radiation. So where do I write alpha? Before or after the arrow? After the arrow. It is going to shoot out alpha. And instead of alpha, I am going to write what? He what? 42. Meaning, uranium originally had 92 protons. And of the 92, 2 are gone. So how many are left? 90 are left. So I'm looking at alpha emission by uranium. And I'm realizing that uranium is my parent, but my daughter is no longer uranium. We've never seen that. We've never seen an element turn into another element. Okay, so this is totally different than what we've seen in the past. Totally different. And if it's atomic number 90, do we have our charts out? Okay, so you need your charts. You find uranium, and then you look at not atomic number 92, but atomic number 90, you have a new element. Which one is it? Thorium. Okay, so I am looking at my chart. This is my parent, and this is my daughter. So the minute I have 90, then I come up with thorium. What specific isotope of thorium do you think will be formed? What did I do? I added 90. I added the 90 plus the 2, and I came up with what? 92. So I want to know what I'm going to write up there. And why 232? 232? And why 234? I'm just repeating whatever you give me. I just want to know the whys. You subtract 4 from? So what do I write up here? 230 what? Make up your mind. 230? 234 plus 4 gives me what? 238. Is that what my periodic chart has? Is my periodic chart has a thorium with a 238? So am I looking at mass number in the periodic chart? Mass number is not in the periodic chart. Okay, let me make that big. Mass number is not in the periodic chart. Did we hear that enough? We said that many times in Module 2 because you kept on wanting to look for that in there, and you're going to want to do the same thing in Module 7. And it's not going to be there. It's not going to be in Module 2 or in Module 7 or in any time period. Okay, so we don't look at the mass number. Those guys are called atomic weights, which are weighted average of all the isotopes taking into account their abundances. That's what those are. Okay, so we don't look at the top number in the chart. Okay, that it's not 234, and that's our answer. Are you with me? Let's pretend we didn't blow this up so much or shrunk it so much. Okay, so I put in here thorium 234. Any questions with this 234 or with this 90? Are we okay? Are we comfortable with those two? Okay, how did you get 90? You subtracted whatever's in the right one side of the arrow needs to be subtracted. It's like if you had the arrow as an equal sign. Just like you did the 92. 92 minus 2 gave me 90. Well, 238 minus 4. And I'm subtracting because it's at the other side of the arrow. I get a what? Okay, so that's, all I'm saying is that 238 is equal to 234 plus 4. That's what I did that. That's my 234. And that's my 4. And that's my 238. Just like I did 92 is 90 plus 2. Yes? Yes. Another question.
Are you always using the helium with alpha?
Always. Helium for alpha. Okay, so this is alpha, this is beta, and this is gamma. Okay, so first we get familiar with the terminology, the different types of radiation. Alpha, beta, gamma are the ones that this course needs for you to learn. Okay, there's more to nuclear chemistry. There's more to any chapter than what we cover here. But these three things you need to know. Alpha, beta, gamma. Okay, so I have it here pretty. But it became too little. Okay, so who was my parent? Uranium-238. And I see that 238. And who's my daughter? Thorium-234. And why do I know it's 234? Because alpha was emitted. Okay? But I don't start up there. I really start down here. If it's uranium, it must be 92. There's many different types of uranium. It so happens that 238 is hot. But if it's uranium, it's 92. And if it's emitting alpha, this guy is out of their nucleus. 2 protons are gone. So how many are left? 90 are left. Are you with me? Okay, so giving you the parent and giving you the type of radiation, you can elucidate what the daughter is. By the same token, if I would have given you the daughter and the type of radiation, could you tell me what the parent is? Like, for example, all we're going to do is add 2 or subtract 2. Okay, so this is what we did. Mass number is 238 minus 4, 234. Atomic number 92 minus 2, 90. That's all we did, yes? Complicated math. This is the easiest chapter ever. I'm not kidding. I'm not kidding at all. Okay, let's do example 4 from page 123. I have my arrow, which is really an equal sign, right? Divides my parent from my daughter. Example 4 on page 123. I have PB is called what? Lead. And on the top I have a 206. And it's emitting alpha, but instead of alpha, I write what? HE. So that's my strategy. I don't write alpha. I write HE42. Because they're the same. And if it's lead, what is the atomic number? What does the chart give you? 82. You all looking at 82 on your periodic chart? Okay, so you must, I know you didn't memorize the periodic chart. You need to look at lead. And that 82 is what I'm talking about. Okay? Notice that I don't have 206 down here because I am not looking for that. Okay, so don't ever look for mass numbers in the chart. Mass numbers are not in the chart. And you're going to write it and write it and write it. Mass numbers are not in the chart and they never will be in the chart. The chart doesn't give you mass numbers. But who's the parent compound? You tell me. Is it this guy? Is it? And in a multiple choice, I'm going to have them all. And you don't go, oh, A. Pretty. Next. You do your little math. Do I subtract now? No, I need to add. 82 plus 2 gives me polonium, which is 84. Okay, so this is atomic number 84 is polonium. And why do I need polonium? Because I am adding 82 plus 2. Okay, so I am adding 82 plus 2. And when I do that, I'm going to come up with, what was it again? 84. So that's step 1. I look at the atomic number. And then if it's 84, I look in my chart. And then I realize that that element must be polonium because I looked in my chart. Okay? And what specific isotope of polonium must have been the parent? 210. And why 210? Because you added what? 206 plus 4 and you came up with 210. Okay, so I can give you the parent, or I can give you the daughter, or I can give you the parent and the daughter. I could have given you this and say, if I don't give you that, Could you have found out what type of radiation it is? Yeah. Okay, so it doesn't matter whether I give you that. Let's try to erase it. Well, that's always a challenge. Okay, so I can give you that, or I can give you whatever. Okay, but they're linked in a very simple way. Let's try to pretend I didn't erase that 2 there. Okay, guys, write a 2 because it's not writing a 2. No me gusta. There. Hallelujah. Got a 2 there. Okay, ready for beta emission? Beta emission. Just as easy. Beta, we're going to relate beta to what? E what? 0 minus 1. That's our strategy. Put alpha as HE42. Put beta as E0 minus 1. Okay, now I am on the next page, page 124, carbon 14. If you look at carbon in your chart, what's the atomic number of carbon? 6. And what is the atomic weight of carbon in your chart? 12. Well, I'm not looking at that guy. Carbon 12 is not of my interest today. Carbon 12 is not hot. Carbon 12 is not radioactive. Carbon 12 is totally stable and totally boring, and it doesn't change. I'm looking at carbon 14. Who's not in your chart? Okay, so your chart doesn't talk about all the isotopes of carbon, nor does it talk about all the isotopes of any element. It doesn't talk about isotopes, period. It doesn't give you mass numbers, period. It turns out that carbon 14 is hot. This guy is radioactive, and it emits beta. So it is emitting, and I'm not going to write beta like this. I will give you beta like that in the test, but I am going to quickly ask you to change it to E0 minus 1. Okay, and where's my step 1? Where am I going to look at? Atomic number. I'm looking at that little number down there, the number of protons down there. That's step 1. What must be the daughter? Okay, and I need for you to look at your charts. If I start with 6, and I'm hearing boron and I'm hearing nitrogen, so make up your mind. No, one of those is not good enough. It's either or. There's only one correct answer. My arrow was equal to what? An equal sign. Okay, so my arrow is an equal sign. 6 equals what minus 1? Is 5 minus 1 6? So could it be boron? So we don't guess. We don't start going, mini, miny, mini, mo. This one looks so pretty. No, we just think, analyze. 7 minus 1 gives me what? 6. So what? After I look at the atomic number, and after finding out what atomic number gives me the correct answer, because now I'm subtracting, then I look at my chart and see what element has atomic number 7. And then I decide that it's nitrogen. What specific isotope, which is just the frosting on the cake, and now I close the chart. I don't even look at the chart because I'm on the top number, 14. So carbon 14 turns into nitrogen after emitting beta. Another example, let's look at example 11. Maybe. In example 11, again, I'm giving you the daughter, beta plus sulfur 32, or sulfur 32 plus beta. It doesn't matter who goes first, who goes second. But what matters is that you need to have a chart out, and I see some of you without it. So unless you've memorized the chart, I don't know how you're getting answers here. If it is sulfur, what is the atomic number? That's step 1. Look at the atomic number. Okay, so I have a periodic chart, and sulfur has a big 16 next to it. That means it has 16 protons. What number do I get if I have 16 minus 1? What is that equal to? What's 16 minus 1? Oh, good. Now I heard nothing but the right answer out, which means we're good. We're all on the same page. 15 is the result from 16 minus 1. And now that I have the atomic number, what do? I look in the chart and find out who the heck is 15. Phosphorus is my man. The isotope. What specific isotope of phosphorus am I talking about? So P32 is hot. P32 is radioactive. P32 emits beta. And in emitting beta, it turns into sulfur 32. That's beta emission. Yes? Are you all with me? Any other questions? Gamma. Gamma emission may occur together with alpha, or may occur together with beta, or may occur by itself. Okay? If it's occurring together with beta, if I have, for example, iodine 131, and I don't give you the atomic number, I just say iodine. Iodine 131. And you translate that like this, and you put what underneath? 53. So you look it up in the chart, and you get that 53. I will not give you the 53. Will not. My test will have this lingo. And you translate it into this lingo. Because that's what we did in Module 2, and you already learned it that way. It's in your head that way. It works that way. So you go to where your comfort zone takes you. This guy emits gamma, which has a 0 and a 0, and beta, which has a what? A 0 and a -1. So tell me who's the daughter. And we don't guess. We look at, what are we looking at now? We look at the 53, the atomic number, and we need a number that which, when we subtract 1 for it, you get 53. So what is it? It must be what? 54. And if it's 54, I go in my chart. I don't know these guys by heart. So 54, maybe, is this guy. Okay, so it's xenon. So I go back. Maybe my screen's dirty because it's not moving. And I put a big xenon here. What specific isotope of xenon am I talking about? 131. Okay? I also have in the book boron with a little star. Boron 11 is hot. And it emits only gamma. Okay, so if it's boron, what's the atomic number for boron? 5. So we're looking at the chart. Now everybody has the chart. Now we're good. So what does it turn into? A stable boron. Okay? So this guy is hot. This guy is stable. And I mean that because I have that little star there. Alright? Are we okay with nuclear reactions? This is the easiest thing ever. So as long as we know how to add 2 or subtract 2 or add 4 or subtract 4 or subtract 1 or add 1, we're good. We don't need a calculator for this one. Yes? The little star means that it's hot. Means it's my parent. Means it's gonna emit either alpha or beta or gamma. It's an unstable. It's a radioactive. Okay? And it's either emitting alpha or beta or gamma or a combination of them. Yes? Okay, if I give you this and I don't give you this part, let's do it again. Let's say I didn't give you that part. I go there and I lasso it and I delete it, maybe. Not sure I want to do that. I'll never be able to get back to where I need to go. Okay, and I say, what particle is going to go there? So what do you tell me? Any one of them. I could ask you for them. Okay, so it has to be right. Okay, so I can give you the parent and the daughter and ask you what particle it is. And there's going to be questions in the test that I'm asking for the alpha, beta, gamma, that I'm asking for the daughter, or that I'm asking for the parent. So you read the question. And I get dozens of students in my office after the test. I can't believe I didn't read it. So please read it. If we know how to add 2 and 4 and subtract 1, let's go ahead and do it and get it right. Okay, so if I'm talking about somebody undergoing nuclear decay, it's this guy, the radioactive fellow. If I'm talking the product of somebody that underwent nuclear decay, I'm talking about the daughter. Okay, so read the language. Yes?
If you ask us for the parent in that case, in that particular case, would we have to put the star?
Baby, you have a multiple choice exam. You don't have to put anything. You just need to pick the right one. So your life is easy.
Correct.
Huh?
It would be the one with the star.
Right. Yeah.
On the test for the iodine, you would give us obviously the parent, and you would give us
No, obviously nothing. I could have had this lassoed. Let's get rid of this guy.
What I meant is, like, if you gave us the parent and then you gave us the daughter, would you give us? How would you ask us whether or not it was a gamma?
Then you would have answered just beta. You don't know that gamma is part of that one.
Okay, so
Okay?
you're not gonna ask
No.
us.
My point here was that gamma is many times not by itself. Gamma comes with alpha or with beta many times. And those are your clues to find your daughter. Yeah? Got it? Okay. Nervous tablets today. All right. Now, your next question should be, okay, so that's all on good. I'm beginning to understand that not every single element in the chart is stable, that some people just, they're hot, they're just shooting out radioactivity. But how long does this process take? How long does carbon-14 take to get to be nitrogen? Carbon-14 turn into nitrogen. How long did that take? How long did P32 take to turn into sulfur? How long did iodine-131 take to turn into xenon? Okay, so those type of questions are answered under the third step of today's class, today's lesson, which is half-life. Okay, so we looked at types of radiation, alpha, beta, gamma, nuclear reactions, and now we're here, half-life. What is half-life? Who read? Who wants to tell me what's half-life? Half-life is, let's pretend we're in college and we want a complete sentence. Half-life is, okay, we're talking too fast. Let me just write very fast. Is the time it takes, okay, the time it takes for half of a radioactive sample, a hot radioactive sample, to undergo nuclear decay. Very good. And you were not reading, right? Okay, so let's translate this into English. What does this mean? Okay, so we're in another area. Now we're looking at time, variable time, and it turns out that the answer for this is what? What is, how long does it take? 5,000 years? Is that what it takes? It depends. If it happens to be, half-life, by the way, is represented, we chemists are very concise. We never write the whole thing. We never write sodium, S-O-D-I-U-M, we write Na. We never write half-life, we write T1 half. Okay, so we're always shrinking stuff. There's just so much to say that we at least say it concisely, but very precise. laser shot. Okay, so if it's cobalt, the half-life of cobalt, cobalt 60, which is used in chemotherapy. My mom died of cancer, and she was treated with cobalt 60. The half-life is 5 years. 5 years. So it's on the order of years. If you're talking about something like P32, we talked about P32. P32 is used to detect tumors. I studied, after my PhD in inorganic chemistry, I went to med school. I think I told you that. And we did cancer research for a while. And cancer is just an uncontrolled growth of cells. And these cells, of course, are replicating DNA. And DNA contains phosphorus. So if you tag HeLa cells, which are cancer cells, with P32, you can see how fast they're growing. Okay, because you can detect it with a Geiger counter. Yeah, we're here, we're there, or where the cancer's moving. P32 is used for detecting tumors, and it has a half-life of 14 days. Things like carbon-14 is used a lot in archaeology. A lot. Very, very widely used. It has a half-life of around 6,000 years. 5,730 years. Iodine 131, which another one of our examples, has a half-life of what? 8 days. And that's used whenever there's thyroid malfunctions. So nuclear chemistry is full of applications. Medicine applies nuclear chemistry. Archaeology applies nuclear chemistry. And every single hot radioactive isotope has its own story to say. This one is used for this, and this one has this lifetime, half-life. And this means what? Okay, so I am flipping pages, and I am on page 126, example C. Example C talks about barium 122. Okay, so notice that I no longer pay attention to the atomic number because I have a chart and I could fill those up any minute that I need to. Barium 122 has a half-life of 2 minutes. Has a half-life of 2 minutes. Okay, so this is my column for half-life. If I start with 80 grams of barium 122, and it is 1:30 in the afternoon, at 1:32, do I still have 80 grams? Nope, I don't think so. I have what? Half of it. Okay, so it's the amount of time that it takes for half of it to decompose. Okay, so how much do I have? What's half of 40? What's half of 80? 40 grams. So 2 minutes after, at 1:32, I no longer have 80 grams, I have 40. What happens 2 minutes after that? Not in the first half-life, but in the second half-life. How many grams do I have? I don't hear you. 20 grams. Good. We had lunch. We speak up. So how many? This was at 1:30 in the afternoon. This is at 1:32 in the afternoon. This was at what? 1:34 in the afternoon. So the clock's ticking. What happens? Okay, so this is 2 minutes plus 2 minutes, which is a total of 4 minutes. What happens 2 minutes after that at 1:36? I have 10 grams, and how many minutes elapsed? 2 plus 2 plus 2, it's 3 half-lives. So I'm multiplying 2 times 3, which gives me 6 minutes. Are we okay with the 6 minutes? Are we okay with the 10 grams? Let's do it a couple times more. What happens 2 minutes after that? Because I want to know how much barium is left after 10 minutes. After 8 minutes, how many grams do I have? 5 grams after 8 minutes. And what about the grand finale after 10 minutes? What do I have? 2.5 grams. So the question was, bless you, starting with 80 grams of barium 122 with a half-life of 2 minutes, how much is left? How much remains after 10 minutes? So you go 2 times 2 times 2 times again and again until you get to your 10 minutes. 2 plus 2 is 4, 2 plus 2 plus 2 is 6, 2 plus 2 plus 2 plus 2 is 8, 2 plus 2 plus 2 plus 2, or 2 times 5. Okay, so 2 is the half-life, and 5 half-lives you had to go through this. Are you okay with this concept? Any questions there? So going forward is good. And guess what? We're now going to flip things around so they sound more interesting. So I'm still on the same page. I'm walking you through example E. And we probably have time for example E and example D, but let's start with example E. Okay, any questions before I start E? Okay, example E is going to give us the relevance of nuclear chemistry in archaeology. When you hear things like, oh, this rock was found, or this fossil was found, or this mummy was found, or this painting was found, and this dates to prehistoric times, or this dates to thousands and thousands and thousands and thousands of years ago. Do you ever wonder, how the heck do they know that? Well, it's this. It's kinetics and it's nuclear chemistry. Living organisms are composed of carbon, and there are primarily 2 types of carbon. Carbon-12, which is stable, it doesn't change, and carbon-14, which is hot. Okay? The ratio of carbon-12 to carbon-14 in living organisms is constant because we're alive and we're keep metabolizing, eating foods, producing more energy from our foods, and carbon-12 to carbon-14 maintains at a constant ratio. Once the organism dies, carbon-14 begins to decay, and you're no longer producing any more carbon-14, so it begins to drop and drop and drop because it's decaying. It's turning into nitrogen-15, but carbon-12 is stable. It doesn't change. So the ratio of carbon-14 to carbon-12 can tell you how old a certain organism is, or a certain rock is, or a certain cave, painting in a cave happens to be. Okay, the half-life for carbon-14 was what? We said it was around 6,000 years. And I gave you specific numbers, because I know you guys love specific numbers of 5,730 years. So every 5,730 years, it gets cut in half. Okay? We can measure radioactive substances. We can take measurements of radioactive substances in units of Curie, in honor of Madame Curie, who discovered radioactivity, the only woman scientist that got not 1 but 2 Nobel Prizes. In becquerels, or in disintegrations per minute, or in disintegrations per second. Bottom line, you put a Geiger counter and you count how many disintegrations are occurring every minute, every second. Okay, so you can measure it in grams, like in this first example, We did from 80 grams to 40 grams, or I could have done it in disintegrations per minute. Okay? A normal piece of charcoal, live charcoal, you just take from a tree. The carbon 14 to carbon 12 ratio is of the order of 13.6. Okay, so disintegrations per minute is 13.6. Now I'm reading example E. A prehistoric cave painting was found in Spain. Somebody found a cave, and inside the cave there were these amazing paintings. And these paintings were done with charcoal. So they took a Geiger counter, they put it next to the paintings, and a piece of charcoal found in this ancient cave in Altamira gave 1.7 disintegrations per minute. So you need to go from 13.6, like we went from 80 grams down to 2.5. We need to go from 13.6 disintegrations per minute all the way down to 1.7. And every time you get it cut in half, a half-life elapsed. 5,780 and 30 years elapsed. Okay? So the question is, how old are these paintings? Okay? So if I cut 13.6 in half, and it takes 5,730 years to do that, what's half of 13.6? What is it? 6.8 disintegrations per minute. That's half-life number 1, the first half-life. A second half-life elapsed. Half-life number 2. So it's 5,780 plus another 5,730. Which gives me how many years? 65, 11. 11,500. Let's make this a long arrow. And 60 years. Half-life number 2. I cut this 6.8 in half. So what do I get? 3.4. All I'm doing is cutting this in half. 13.2 divided by 2 is this. 6.8 divided by 2 is this. And if I divide this fellow by 2, what do I get? 1.7, which is what this painting was giving me. I put this Geiger counter and this piece of charcoal, and it gave me 1.7 disintegrations per minute. So a third half-life must have elapsed. So I need to add another 5,730 years to it. So I come up with what? 17,190 years old. So it's not that somebody was there in the painting and said like, yeah, I'm 17,000 years old, and I saw when this guy painted this thing 17,000 years ago. We just use our brain, we use knowledge of chemistry, kinetics, studies, the rates of reactions, and nuclear chemistry, put it all together, and you come up with wonderful findings. Are we okay with that one? Okay, so you can hear things like this mummy was from the Neolithic period, or this thing is 20,000 years old, or this rock or this fossil is gazillion years old, and this is how they do it. Okay, let's do example D.
So we have to memorize 13.6 disintegrations per minute per gram.
No. You need to know the concept, because I will ask you the concept forward and backwards and inside out. Let's just do one more. Example D. I have, on page 126, example D. I have 10 milligrams of iodine, 131. And iodine 131 has a half-life of 8 days. So knowing that the half-life of iodine 131 is 8 days, and I'm giving this patient 10 milligrams because this patient has thyroid problems, and I need to measure thyroid data. I want to know after 24 days, how much of this radioactive iodine-131 is left with the patient? How do you do this? Okay, if the half-life is 8 days, how much is left? How much iodine-131 is left after 24 days? Okay, and the letter examples, we don't look at the answers. Yes, the answers are there, and I don't want them. I want my brain to work. So what do? You tell me. Divide the 10 by 2. So I start with 10 milligrams, and I divide it by 2, and I get what?
5.
And how many days does that take? So that's my first half-life, 8 days. So I'm writing the 10 milligrams. So I can write this in degrees per minute, or grams, or milligrams, or whatever amount I'll start with. And then I write the time and the half-lives. 3 things, yes? Then what? I cut the 5 in half again, because I need to go all the way to 24 days, not 8 days. So half-life number 2, how many days is that? 8 plus 8, 16 days later. How much iodine-131 is this patient going to have? 2.5 milligrams. Did I make it to 24 yet? So what do? I cut the 2.5 milligrams in half again, and what do I get? 1.25 milligrams. How long does it take for me to get to 1.25 milligrams? How many half-lives? 3 half-lives. How many days? 24 days. Is that what they wanted? So what's my answer? 125 milligrams. Yes? Not so bad? Ready to tackle 7 full blast today? Okay. So have a wonderful day. We learned about alpha, beta, gamma, nuclear reactions, and half-life. Just come see me if you have questions.